Hello, today we are starting exponential functions. It's section 4.2 in your book. So first of all, let's define exponential function. An exponential function is a function provided b is a constant real number, b is positive and b is not equal to 1. Then for any real number x is the variable, the function of the form f of x is equal to b raised to power x. Now what do we know? B is a positive number and b is not equal to 1. Then this is called an exponential function with base b. B is called the base is b. Let's see a few examples of exponential functions. If we have say 4 raised to power x, that would be an example of exponential function. The base is 4. If we have 0.2 raised to power x. That is also an exponential function. The base is more than 0, it's not equal to 1. That is 0.2. If we have, say, 1 by 5 raised to power x, that's also an exponential function. The base is 5. If we have, say, square root of 2 raised to power x, that is an exponential function with the base is square root of 2. What are some example of not exponential functions? If I say, for example, negative 2 raised to power x is not exponential because negative 2 is less than 0. We want our base to be a positive number, right? So this is not an exponential function. Or say we have x square. The base has to be a constant real number, which is, remember, the base has to be a constant real number, which is positive and not equal to 1. So, base not constant. So, this is not a rational exponential function. Or 1 raised to power x is not exponential because base is equal to 1. We cannot have that. Okay, the base is not equal to 1. It is a constant number and it is positive. It also cannot be negative number. Now let's see how can we graph this kind of function. I'm going to take this as an example. If we have 2 raised to power x and I want to graph it, I want to draw a table of values for that. For any graphing function, I draw a table of values and then I draw a graph. So I can take some x values. For that, I will get y, which is equal to f of x, which is 2 raised to power x. Let's say x value is 0. Then 2 raised to power 0 would be 1. Let's say x is 1. Then 2 raised to power 1 would be 2. Let's say x is 2. Then 2 raised to power 2 would be 4. X is 3, 2 cube would be 8. What if x is negative 1? X can be any real number. 2 raised to power negative 1 would be half. Negative 2, 2 raised to power negative 2 would be 1/4, and so on. So if you notice what's happening as x is approaching to negative side, negative infinity, it's getting smaller and smaller. As x is approaching to positive infinity, it is getting larger and larger. Let's try to draw the graph of this function. This is x-axis. This is our y-axis. Let's say we have 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, 1, 2, 3, 4. This is your grid. Now, what do we have? The point at negative 2, function's value is 1/4. So somewhere here. At 1, negative 1, function's value is half. At 0, function's value is 1. So this is an important point. An exponential function always at 0 is always 1. At 1 it is 2. At 2 it is 4. At 3, it is very high, somewhere here, say 8. So if I have to draw a curve through this, the curve is going close to 0 as x approaches to negative infinity. It's going really high as x is approaching to infinity. This is the graph of the function 2 raised to power x. So what do you notice about this curve? The curve is approaching to infinity as x is approaching to infinity, is increasing exponentially. As x is approaching to negative infinity, the curve is almost approaching to 0. The graph always stay above x-axis, right? So I'm going to say domain of this function is all negative infinity to infinity. Because domain is x values, this function is defined for all x values. Range is y values. It is always staying above 0 and then it is approaching towards infinity. The lowest value of y, it is never taking 0 value, but it is staying above. Y-intercept is equal to, at 0, y value is 1. Y-axis intercept is always at 1. Okay. And x-axis is looking like an asymptote. X-axis is a horizontal asymptote. Let's look at another graph, another example, then we'll compare them. The function is g of x is equal to half raised to power x. Let's say y is equal to g of x, which is half raised to power x. You can also think of it as 2 raised to power negative x. Okay. So both of them are one and the same thing. So for plotting this graph, I have to draw table of values, obviously. So let's say x, y is equal to half raised to power x. Let's say x is 0. Half raised to power 0 would be 1. At 1, it would be half. At 2, half raised to power 2 would be 1/4. At 3, it will be 1/8. At negative 1, when you do negative 1, negative power, it flips, reciprocates. So half raised to power negative 1 would be 2. At negative 2, it will be 4. So what do you notice if I have to plot the graph of this function? Let's have a grid. At 0, the value is 1. At negative 1, the value is 2. At negative 2, value is 4. At negative 3, it will be 8. At 1, it is half. At 2, it is 1/4. At 3, it will be 1/8. So as you notice, what's happening? As x is approaching to negative infinity, y is approaching to infinity. As x is approaching to positive infinity, y is approaching to 0. So if you join all these points, the curve is gonna look like a smooth curve going like that. So what is the difference this curve when the base was 2, which is more than 1? If base is more than 1, then it was a increasing graph. In this case, let's notice all the same parameters. Domain is still the same, negative infinity to infinity. Range is still the same. The graph is staying above x-axis and it's approaching towards infinity. Your y-intercept is still the same. At 0, the value is 1. Then we have x-axis is still the horizontal asymptote. And base in this case is half, which is less than 1. and the graph, if you notice, is decreasing graph. Decreasing graph means x values, as x values are increasing, the y values kept on decreasing. So these examples I took specially because we can analyze them as two specific cases of exponential functions. First case, when the base is, this function is a raised to power x, this graph is a raised to power x, base is more than 1. This function is also a raised to power x, but base is less than 1, and always it has to be more than 0. Let's notice what we know. The graph of the exponential function, if base is more than 1, is always above x-axis. That's true for both of them. Doesn't matter base is more than 1 or less than 1. Y-intercept is always 1. That means when x is 0, the graph is passing through 1. That is true for both of them. Either the base is 1, less than 1, or more than 1. The graph climbs steeply to right if the base is more than 1, but graph falls sharply to the right if base is less than 1. This is the difference, okay? This is the important point. The graph is increasing graph if base more than 1. Graph is decreasing graph if the base is less than 1. X-axis is the horizontal asymptote, negative side of x-axis, and positive x-axis is the horizontal asymptote. Now, here are one more important fact. Larger the base is, more steeply the graph will rise. So what I'm trying to say here is, say we have 2 raised to power x. Let's say the graph of 2 raised to power x is this. Let's say this is 2 raised to power x. If we would to plot 3 raised to power x, then if the base is larger, then it will rise steeper. So this would be 3 raised to power x. Say I have 4 raised to power x. That would be even steeper. So 4 raised to power x. Larger the base, more steeply the graph rises to the right. Now let's look at the right side. It says smaller the base, the more steeply the graph falls to the right. Let's say this given graph is this half raised to power x. Okay. What if half is what? 0.5. What if we have 0.4? The smaller the base, then the graph falls steeply to the right. This would be 0.4 raised to power x. If I have say 0.7, then it would be a little less steeper than half raised to power x. This would be 0.7 raised to power x. So smaller the base, more steeply the graph falls to the right. So these are the basic observations from the exponential function. These are the important points.